So, dear participants of our conference, with my big pleasure and honor, let me introduce our next speaker today, Vyacheslav Futorny from University of São Paulo and University of University of Shenzhen. He will tell us about Krichever-Novikov algebras and orthogonal polynomials.
Thank you very much, Oksana, for the introduction. Yeah, let me share the screen. How to open the...
Not a full screen, only a short part.
Now it's good?
It's good, yes. Thank you.
Okay, so it is a great pleasure for me to participate in the 15th Ukraine Algebra Conference. And it's a real honor and pleasure. So I'm going to talk about Krichever-Novikov algebras and related orthogonal polynomials. Let me start first recording the concept of so-called map-Lie algebras. So suppose we have a simple finite dimensional Lie algebra over complex numbers and a unital commutative associative algebra A. Then we can take a tensor product of these two algebras as vector spaces. And this vector space will have a Lie algebra structure with respect to a natural Lie bracket. So if we take a Lie bracket of two tensors, then we take a Lie bracket of x and y, the left parts, which is the operation in the Lie algebra, and then tensor with the product of the right parts, which is the product in algebra A. Now, this is so-called map-Lie algebra, which defined, this very general setup for any finite dimensional simple Lie algebra G, or for any Lie algebra G, in fact, and any commutative associative algebra A. And this is the Lie algebra of maps from the spec of A to with the values in G. There are many examples of such algebras. So one special case is the case when the algebra consists of Laurent polynomials. Then the resulting tensor product is called the loop algebra. And there's a base for the construction of non-twisted affine Kac-Moody algebras, which is just the universal central extension of the loop algebra. And with the Lie bracket, so this universal central extension in this case is one-dimensional. So we have this just one central element K. And the Lie bracket changes because of the cocycle, so we have additional term here. So unfortunately, here I had pictures of the creators of Kac-Moody algebras, Victor Katz and Robert Moody, but unfortunately, in this file, they disappeared. So these are non-twisted affine Kac-Moody algebra. Of course, there is a second part of the theory consisting of twisted ones, but I'm not going to talk about them today. And sometimes in the definition, in the construction of affine Kac-Moody algebra, we add the degree derivation. So one more element that goes to the Cartan subalgebra of affine Kac-Moody algebra, and that takes care of the derivation of the grading, extra grading on our algebra and on the corresponding representations. The second example of the second family of examples of such cases is the following. So suppose we have an affine algebraic variety X in the affine space and dimensional affine space, determined by a set of polynomials G1, Gm in some number of variables x1, xn. And so these polynomials define an ideal vanishing on X. And then as an algebra A, we take the quotient of the polynomial ring by this ideal. So these are polynomial functions on X. And then we can consider the tensor product with a given finite dimensional Lie algebra. You can always think of SL2 for simplicity. Yeah, 3 by 3, 2 by 2 matrices with trace 0. And this family of examples may be especially interesting if we consider a different construction of infinite dimensional Lie algebra starting from a finite dimensional one and starting from this algebra A, in fact. So if we take derivation of A, so derivations of A form an infinite dimensional, in general, Lie algebra with respect to the bracket given by the composition of derivations minus the composition of derivations in the inverse order. And this becomes a Lie algebra, and this is the source of a large number of simple infinite dimensional Lie algebras. So such Lie algebra will be simple if and only if the variety X is smooth. Coming back to our construction of map Lie algebras, in general, they are not simple. So that's more complicated, but both families, G tensor A and derivations of A, are sort of the main tools constructing infinite dimensional Lie algebra from finite dimensional and commutative algebras. And this family, the family 2, is related to the next example, the next family of examples of Krichever-Novikov algebras. So these algebras were introduced by Krichever-Novikov in their study of conformal field theory in Minkowski space. And they start with a compact Riemann surface and the set and fixed set of points. And this will be the points where we allow the poles. And then we consider the ring of meromorphic functions on X. And the poles of these functions are allowed exactly in this designated set chosen set P. And then the tensor product is the Krichever-Novikov algebra, G tensor A. In fact, the derivations of A also can be considered as a Krichever-Novikov algebra in a more generalized sense. And I'm not going to talk about the theory of these algebras, which is quite developed now. I will just refer to a beautiful survey in a book by Martin Schleichenmeyer, where he describes the origin, the structure of Krichever-Novikov algebras, their representation theory, and all possible generalizations. The first example that I mentioned of Laurent polynomials in one variable corresponds to meromorphic functions on the Riemann sphere, where we allow poles in 2 points, 0 and infinity. Right? So this is the simplest possible case as a gene is 0. So suppose we move to the next level, to elliptic curve. And so suppose that's denoted by X such elliptic curve. So this is genus 1 case. We identify it with the quotient of the complex plane by the Z lattice with the basis 0 lambda. And our algebra A, or ring A of meromorphic functions, consists of functions which are holomorphic outside of 2 points, 0 and this another value determined by lambda. So this case was studied by Bremner in 1994, and he realized that the algebra of this algebra of meromorphic functions can be identified with the following ring: the Laurent polynomials in variable t and polynomials in U, subject to this elliptic equation. Yeah, U square equals t cubed minus 2bt square plus t, where b is a certain parameter determined by the Weierstrass function. So we see that we have a link between the third family and the second family of examples above. So naturally, starting from this elliptic equation, we can go to a more general equation, hyperelliptic curves, when we have the ring A is determined by the equation u square equals any polynomial p. And these examples were considered by many people before. For example, here, Bremner and Cox considered the quadratic case when p is quadratic. Cox, Jurisic also considered quadratic. So the difference is that the polynomial vanishing at zero or not in the first case. And in our work with Ben Cox and Juan Tirao, we consider the case of the polynomial p of degree 4. And then I will mention this below. And of course, we can go generalize further. We can consider the equation which determines our curve, the m's power of u, an arbitrary polynomial p of t. So some examples were considered before. So it's like cubic in u and cubic in t by Bremner, and then cubic in u and degree 4 in t, Albino dos Santos. And then just recently, we consider arbitrary power of u and degree 4 of t with my Brazilian colleagues. Okay, so suppose we have such a situation. So here's the picture just to show their relations. So suppose we have such a ring and we have a tensor product with algebra G. And now we consider the universal central extension. Remember, like we did in the construction of affine Cos-Moody algebras. In that case, it was one-dimensional. In general, the universal central extension is determined by the Euler differentials modulo the exact forms. That's the result of Kassel. So to construct omega 1, so one forms, we start with the tensor product of the algebra of functions A and consider it with itself and consider it as a left module over itself with a natural action. And then we take a submodule, a quotient by a submodule generated by these elements. This is omega 1, and then we need to take the quotient by the exact forms. So this is the universal central extension. In our setting, it has a dimension 2g plus n minus 1, where g is a genus and n is a number of poles. So since this space, this quotient is finite dimensional, then so if we choose a basis, and then naturally we will have many linear dependencies between the differential forms. And in particular, there is this general congruence modulo dA between the forms. It doesn't matter right now what the coefficients are, but just to show that there are linear dependencies between the differential forms. And that they will be important for us below. So in 1995, Bremner showed that for the ring, which is Laurent polynomials in variable t and polynomials in u, with the relation determined by the equation u square equals arbitrary polynomial p, the following forms or the images modulo the exact forms, or one forms, they form a basis. Right? So he explicitly wrote the basis. And then particular cases of these constructions were considered. For example, when P has degree 2, in this case, we have two-dimensional center. So these two elements form a basis. In the case when we have this polynomial relation, we have dimension of the center will be 3. So we have these three elements of the basis. And in the case when we have a cubic polynomial on the right, so we have also three elements of the basis, basis central elements of the central extension. So these different cases have own names like 3-point affine algebra, 4-point affine algebra, and so on. So many examples were considered. This is just to illustrate what the central extension looks like in some cases. So if we continue this last case, yeah, this is elliptic equation. So if we look carefully, what is the linear dependence between the one forms? And so then it will look like that. This red formula shows the linear dependence. And the coefficients will appear in front on the right-hand side, that's P and Q, and they depend on B. Now, let's think of this P. Let's consider them separately and think of P as functions of some variable B, let's treat B as a variable. Then we will get the following recurrent relation. So if P is think of this as a polynomial expression in B. B is a variable, and then this family of polynomials indexed by non-negative integers, they satisfy these recurrent relations. So what kind of polynomials we get? Well, to solve the recurrent relation, we need some initial conditions. So we assign these values. Well, it turns out that these polynomials are famous orthogonal polynomials, which have a name Polyachik. So the Polyachik polynomials, their generating function, as this series, satisfies this differential equation. So this is quite curious. It was the first time observed that there is an interesting relation between certain families of orthogonal polynomials and universal central extensions of Krichever-Novikov algebras. Then second example of this kind was for this Krichever-Novikov algebra. So when we take as a ring A, Laurent polynomials in T and polynomials in U with this relation between U and T, right? So we have a degree 4 polynomial on the right-hand side. So this algebra is called Data-Jimba Kashiwara-Miwa algebra. So it was introduced by these authors in their study on the solutions of Landau-Lifshitz equation that looks like that and describes the movement in the magnetic field. So then they introduced this algebraic model related to this physical model. And the universal central extension in this case is 5-dimensional. So with Ben Cox, we established this long ago that it is a 5-dimensional central extension. And then again, we can ask, can we find some polynomials, orthogonal polynomials related to this universal central extension? Well, let's look carefully. After some renormalization, we can get the following relation. This is a linear dependence between the one forms. Now, let's consider a family of polynomials that depend on the variable, some variable C. And then they will satisfy this from the red formula, we write the recurrent relation. And we ask, okay, so now we have a family of polynomials in one variable that satisfy this recurrent relation. What can we say about them? Well, if we look at the generating function of these polynomials, so just write a series in powers of variable z, then it will satisfy this differential equation. So because we have a recurrent relation, so we need some initial conditions. And we need 4 values, right, to solve the recurrent relations, we need to assign 4 values to the first 4 terms. And usually we assign 1 to one of them and 0 to the others. And then so we have 4 possibilities, depending to which one we assign the value 1. And these cases are quite different. So the first case, the generating function looks like that. And this is an elliptic integral, so we cannot find it. The second one is also, but the third and fourth, right? So these are the cases when we assign 1, the value 1 to these terms. The third and fourth case, we can solve, and we can write the generating function in terms of Gegenbauer polynomials, this Gegenbauer polynomials Q. And this generating function satisfies the second degree differential equation. So the Gegenbauer polynomials, it's a family of orthogonal polynomials, classical orthogonal polynomials. So both families that I mentioned, Polyachek and Gegenbauer, are classical orthogonal polynomials satisfying the second order degree differential equation. What about the first 2 cases with elliptic integrals? So for example, the first one, we can write a few terms, first terms, just to have an idea what it looks like. And then long ago with Ben Cox and Juan Tirao, we showed that both cases, in fact, give rise to the families of orthogonal polynomials. But let's do it step by step. So first, the first family satisfies this differential equation of degree 4. Okay, so it by itself, it does not imply anything yet, right? And so the second family satisfies this differential equation of degree 4. Now, does it mean, how do we check that they are orthogonal? And if orthogonal, how do we check whether they are classical or not? Well, it turned out, long story short, it turned out that these families of polynomials that we discuss belong to the family of associated ultraspherical polynomials, which are known to be orthogonal with respect to some weight function. Weight function means that it's not integral of the product of 2 polynomials 0, but you need to multiply by certain weight function. And this was introduced by Wimb, Bustos, and Ismail. So since they associate ultraspherical polynomials, so we know that they are orthogonal and they are not classical. Okay, but the story was a little bit different. So we proved, in fact, before knowing these results, special functions, we proved directly their orthogonality using the Favart theorem. So Favart theorem says the following, that if we have a recurrent relation for the family of polynomials, and the coefficients are some complex parameters, then these polynomials form an orthogonal family with respect to some function if the coefficient satisfies such condition. And then in our case, it's exactly happens. So from here, we deduced that they are orthogonal. Now, classical or not? So it is known that classical orthogonal polynomials satisfy the degree 2 differential equation, which means there is a differential operator of degree 2 like that, which annihilate our polynomials. That's in the classical case. And then checking, this is not true for our family polynomials. So we know that by Favart theorem, they are orthogonal, and on the other hand, they are not classical. So this is a kind of, again, now we know that they are ultraspherical associated polynomials. So why I'm saying about this Favart theorem and how to prove in practice, because our hope still is that, considering the universal central extensions of Krichever-Novikov algebras, we might find a family of orthogonal polynomials which is outside of the family of associated ultraspherical polynomials, and hence discover some new families of orthogonal polynomials. And then we will need to use this technique. So we tried to apply it in the case of superelliptic curves, right? So we have, first of all, Albino dos Santos, so my former student, PhD student, proved the following, that if in this general setup, the universal central extension will have this basis, and hence the dimension of this universal central extension will be this number in terms of the powers of u and t, or these numbers, depending if we have or don't have a free coefficient. And then we looked in details in the case when m is arbitrary, but n is 4. And our conjecture was that we should get a degree 6 differential equation. Hopefully, orthogonal polynomials satisfying degree 6 differential equation. So the degree should go up. Well, it did not happen. In fact, the degree of the differential equation stayed, the order of differential equation stayed the same. So for this, in this case, we have such a linear dependence, which brings us to such a recurrent relation between the families of between the polynomials of our family, right? And then we try to solve it. So again, we need some initial conditions. So for example, and we were trying to follow the same scheme as in the case of m equals 2 case. Yeah, the Data-Jimbo-Kashiwara-Miwa algebra. The generating function will look like that, right? It's a quite unpleasant integral. Nevertheless, we were able to show recently that this polynomial satisfies such differential equation of degree of order 4. Okay, so then there is that was so a very unfortunate case, because we hope to get higher order, but still we get degree 4. And in fact, we were able to check that. First of all, we can prove that the generating function satisfies this partial differential equation of degree 4. Yeah, in spite of the fact that we cannot compute the integral, we were able to find the differential equation for the generating function. And similarly, for the second family, again, the recurrent relation looks like that. And then we found the differential equation of degree 4 satisfied by our family, the second family of polynomials. So we have two families of polynomials that satisfy degree 4 differential equation, which again does not imply anything, but if they are orthogonal, then they are not classical. And in fact, we were able to show that they are ultraspherical, associated ultraspherical polynomials. So they're new families. And then, so we have m is a parameter. So for arbitrary power of u and degree 4 t, so we got this one parameter family of associated ultraspherical polynomials that satisfy the differential equation of degree 4. So unfortunately, we could not get higher degrees, but now then we thought, okay, maybe we should increase the degree of t. On the right-hand side, we consider polynomial of larger degree, and then maybe the order of differential equation will go up. Well, so far it did not happen. We have not covered all the cases, but considered many polynomials of arbitrary degree essentially on the right-hand side. And so far, the differential equation stays of degree 4. So most likely, they all will be associated ultraspherical polynomials there. But the curious fact remains that there is a strong relation between the universal central extension of Krichever-Novikov algebra and non-classical orthogonal, well, some classical, because choosing the value, different values for initial conditions, we get classical polynomials like Polyachik and Gegenbauer. So these are particular cases. But also we get a non-classical orthogonal polynomials that satisfy degree 4. The quest continues. So now we are thinking to consider more general rings. It's not corresponding to algebraic curves, but maybe the product of algebraic curves, and hoping to get differential equation or to understand the correspondence between the order of differential equation and such varieties. And so besides an interesting correspondence between universal central extensions and orthogonal polynomials, the main message that I want to say is the following. Якщо деякі студенти слухають мою доповідь, я хочу сказати таке. Я не любив диференціальні рівняння на другому курсі в університеті. І потім повинен був вивчити знову все це з нуля. Тому не потрібно нехтувати диференційними рівняннями або аналізом, навіть якщо наше серце належить до алгебри. Дуже дякую. Thank you very much.